I really enjoyed the day myself yesterday. So we have a number of exciting talks today as well, and finishing up with the forum tomorrow. I want to put a plug in right now for the meeting on the Global Exploration Roadmap on Thursday. I know about half of you checked the box saying you intended to stay, so that promises to be a good meeting. We have some people that are going to be piped in from Europe for that. I wanted to just make a couple of very quick announcements, and then we can get started with the program today. First of all, for those who haven't been in, I really want to encourage you to see the LMMP demo, which is, gosh, I don't remember what room it's in, but it's on your little map here. 112. Thanks, Brian. So it's pretty cool. They have a really neat table. All I can say is I want one. So anyway, it's a really nice demo. So I encourage you to see it. And then I also strongly encourage you to order your sandwiches. The sooner the better. With that, I'd like to go ahead and get started with the program. And it's my pleasure to introduce Joe Lazio, who is going to give an overview talk entitled 50 Years of Exploration Science with the Deep Space Network. And this is an invited talk. Joe.
Thank you, Greg. Testing. Can you hear me? Yes? No? Testing. 1, 2. Can you hear me now? Sort of. Is that any better? That sounds better. Okay. Okay, it is a great pleasure to be back here at the Exploration Science Forum. It's both a privilege and a challenge to summarize 50 years of history in 15 minutes, but I will do my best. Let me start in a nutshell. My aim this morning is to remind you that the Deep Space Network has been an integral part of exploration science for the past 50 years. It has been, it is, and it will continue to be an integral partner in exploration science. What is the Deep Space Network? The Deep Space Network is a network of 3 ground complexes. At each ground complex, there are multiple antennas. This is the primary spigot through which all planetary data flows. It is a partner with nearly 3 dozen planetary science missions. That's both NASA and our international partners. And at each, as I've already indicated, at each complex, there are multiple antennas. There are at least 2 34-meter antennas at each, as well as each one having one 70-meter antenna. And of course, since the World Cup has just concluded, I'll remind you that 70 meters is comparable to the scale of a football field. So these are very massive antennas, precisely designed to bring down lots of data from very distant spacecraft. One of the reasons I'm here is that Christmas Eve in 1963, then director of JPL, William Pickering, formally established the Deep Space Network, pulling together a few disparate elements. From a single antenna, it's now grown to that worldwide complex of 3 ground stations. And of course, the other notable aspect of this formal establishment, and why we're in our 50th year of celebration, but one of the other notable aspects is, this tradition of having important mission events happen on or near major holidays started early. I'll remind you as well, in 1963, what was the state of communications? We were already in 1963 talking about interplanetary spacecraft, and yet the hotline to Washington and Moscow was more a teletype. And should you have tried to call, say, relatives in Europe or in another country, international communications were a bit iffy. I can't state anything about 1963 without acknowledging there were some very sobering events during it. But there were also, shall we say, more interesting events. We learned to appreciate French cooking. And from the perspective of exploration science, 1963 was an important year in NASA's history because NASA was making the transition. This is Gordon Cooper and the Faith 7, the last of the Mercury missions. NASA was making that transition from suborbital flights to a directed focus of exploration of the moon. One of the key aspects of that is then you've got to be able to get your spacecraft to the moon. You want to characterize the surface before you get there. The first successful, certainly U.S. successful mission to the moon was Ranger. And you see here the images from Ranger 7 as it approached and then ultimately hard landed, as it were. I can show you these pictures. because they came down through the Deep Space Network. We had a way not only of sending the spacecraft there, but actually getting the data back. And just getting the spacecraft there, a key aspect of the DSN is navigation. So how do we navigate? How do we form a trajectory from point A, say where we are today, to the moon or some other target? The other thing I should point out about this is, of course, we just celebrated the Apollo 11 anniversary. The Ranger 7 impact was, I guess, about 10 days from now on July 31st, and that's also coincident with, I believe, it's the Apollo 15 landing. Moving forward from the first robotic missions to the moon to finally the Apollo astronauts, Apollo from the science perspective was an impressive return. The astronauts brought back those rocks. That really helped solidify, perhaps no pun intended, the giant impact model for the origin of the moon. There was the first placement of a telescope on the moon, a far ultraviolet Cameron spectrograph. And importantly, I can show you these images, and we can talk about that kind of thing, because there was communication and there was tracking provided in large part by the Deep Space Network. Okay, that was then. We've done 50 years of that. What are we doing today? Or what are the kinds of exploration science that the DSN is supporting today? Perhaps you remember a few years ago, the LCROSS spacecraft was intentionally crashed into the south pole of the moon. Completely crazy idea, right? Why do you crash a perfectly good spacecraft into the south pole of the moon? Well, the idea is to test this hypothesis that there is water at the south pole of the moon. Where did that hypothesis originate? It originated from anomalous radar returns provided by the Deep Space Network and then our partners at the Arecibo Observatory, showing that the South Pole, even though the Apollo rock samples are extremely dry, that there is in fact anomalous radar returns consistent with there being ice in the South Pole, and that helped motivate or helped really strengthen the idea of the LCROSS mission. Moving outward, continuing on the radar theme, and this is actually now a video that I believe will start up momentarily. The radar system that's on the 70 meters antenna, the 70 meter antenna, well, okay, it's gone to the video, but the 70 meter antenna out at Goldstone has a radar system attached to it, which has been an integral part of studying asteroids. So what you see here, if the video was playing, what you see here is 1998 QE2. The thing that jumps out, obviously, is a moon. So one of the key ways of identifying that asteroids have moons is through radar. This, of course, immediately gives us the mass. And I'm going to jump back to the slide now. And in fact, in general, in terms of characterizing asteroids, radar has been an integral component of that in terms of orbit determination, rotation periods. The other thing I should say, we have not yet perfected time travel, but if you were at Lance Benner's talk yesterday, he provided much more detail on how radar has been an integral aspect of characterizing the Earth asteroids. And I believe slides are going up, so if you didn't get a chance to see his talk, you'll have an opportunity to look back at the slides. And other examples of characterizing asteroids and moving into smaller and smaller bodies. Here are a couple of asteroids, and the key point here is that the Goldstone Solar System radar is now routinely getting down to less than 200 meter diameter objects. This object, YU55, is interesting. I bet you can't see, but there are some bright specks through here. Those are real surface features. So we're getting to the point where you can actually characterize the surface. That's, of course, interesting not only from the science perspective, but one of the ARM options is to go pick up a rock off the surface of an asteroid. And should that option survive, characterizing the target body surface is going to be an integral aspect of that. And then finally, from the standpoint of the other reason we're interested in asteroids is hazard detection. This is 2012 GA14. One of the reasons we use the radar for studying asteroids is because as soon as you light the thing up, you get a very precise orbit determination. All of the objects that I've shown you, we're assured they're not going to hit the Earth in the next decade or next century. This one is notable. It got a lot of press, I guess about a year and a half ago, because it came within its orbit, or its trajectory took it within the geo belt, the geosynchronous belt of spacecraft. And of course, it would have gotten even more press. Well, the other animation, yeah, it would have gotten even more press, except for the fact that this thing exploded over Russia, coincidentally on the same day. We've actually been to an asteroid. And again, the near Shoemaker mission went to Eros, or 433 Eros. It did I believe at the time the mission was developed, it was not scheduled, it was not designed to do a soft landing, but because we had the DSN and we could do dynamic reprogramming, as it were, command the spacecraft, it did actually touch down. You can see images brought back through the DSN. So examples of how the DSN has been integral to characterizing these asteroids and helping to understand their properties. The other aspect in which the DSN has been important, and this was recognized in the very early days, is that as you have signals, as you have a spacecraft that's near a planet, as the signals go near the planet, and this example is showing us a planet with an atmosphere, the signal characteristics can be changed. And you could say, oh, well, wow, my communications with the spacecraft have been interrupted and this is a bad thing. Or you can say, and the animations are not appearing easily here, or you could say that, look, if I can understand how the object is changing the characteristics of the signal, I can learn something about the object. So not only perhaps in a simple example of the atmosphere, but you can actually probe the interior of a body. You effectively turn the spacecraft and the DSN antenna into one giant science instrument. The epitome of this is perhaps the Grail mission, which instead of a spacecraft and a ground antenna, we now have two spacecraft that are precisely monitoring their separations, as well as being tracked by the DSN. And you get this wonderful lunar gravity map. Of course, when it's combined with lunar laser ranging, you then get deep probes into the moon's interior. And again, all of this is essentially taking the concept of radio science and making the DSN and a spacecraft into a science instrument, and is, as it were, perhaps putting it on steroids. Looking at the moons of Mars, Mars Express, which is an ESA mission, was linked up with a DSN antenna to do one of these radio science experiments. Mars Express has actually done several close flybys of Phobos, and in the process of doing those close flybys, they've been able to start probing the gravity field of Phobos. And the interesting thing, when I was a boy, it was quite clear that Phobos was a weird object. The standard hypothesis was that it was a captured asteroid. But the interior characteristics of Phobos, at least the team that analyzed these radio science data, it appears to be very porous. And the competing model that they've put up, and I'm not sure it's going to show up, I'm not sure it shows up well, but essentially that there's a belt of debris around Mars, and Phobos reaccreted in place. It's not a captured asteroid, but the amount of porosity on the interior suggests that it had to, in some sense, reaccreted in place. Perhaps similar to the moon, the way the moon did from a belt of debris, but with the boulders remaining more intact as opposed to forming one solid object as in the moon. So when I give the public talks, the punchline out of this is when I was a boy, Pluto was a planet, Phobos was a captured asteroid, and neither of those is true today. Again, all brought to you by the DSN. Now, for the next 50 years, well, your crystal ball, my crystal ball is no better than yours. I think the one thing I will say with some certainty is I think the planetary science community has done a remarkable job of characterizing what its community goals are and setting priorities, and I expect that to continue through the decadal science process. And of course, the missions that are designed are going to have the DSN as an integral component of them, both to get the spacecraft where we want them to go, as well as to bring the data back. But there are other things that you could imagine. What are the kinds of advances that we might expect, say, over the next 50 years, particularly in the context of the kinds of bodies and missions that Survey and Survey mission might be interested in. One thing that I think is particularly intriguing is this entire concept of small sats or CubeSats. Here you see a few, actually a small fleet, as it were, 3 that were ejected out around the Earth. The EM1 mission, which is the first actually test flight of the Orion crew vehicle, is scheduled to have a CubeSat called Lunar Flashlight going to the moon and a CubeSat called NeoScout going to a near-Earth object. So a nice melding between the science or the kinds of characterization that one wants to do on the science side of Survey, as well as melding that with the exploration. I think from a science perspective, this is very exciting. We've sort of done the onesies and the twosies spacecraft at planets or at asteroids, right? Now we should be thinking about fleets, and whether that's fleets of spacecraft at planets or a fleet of spacecraft going out to asteroids. Well, I can remain agnostic about that, but from the DSN perspective, this is interesting because it's starting to cause us to think about new ways to operate the DSN. But I think it's an invigorating challenge to help bring back some of the science. This graph is intended to illustrate data rates and put some quantitative numbers associated with it. Over here is about 10 kilobits per second. On the other side is 100 megabits per second out to a gigabit per second. Well, on the top part of the graphics are not, the animations are not responding the way I anticipated, so I'm going to have to walk you through this. The top part here is data for science. So this is the kind of thing, many of the figures and posters that we see today are scientific data brought down. And the bottom is data for exploration, the sense of being there, and whether it's astronauts telerobotically operating something, or school children talking to astronauts, or astronauts talking to their families. What you want to do is we want to be out in this corner of the diagram. We want to be able to deliver, I think from the science perspective, we should be saying we want to be able to characterize and study these other objects in the solar system with the same kind of data that we use to study our home planet. So something like synthetic aperture radars, hyperspectral imagers, and that pushes you out into the tens, hundreds of megabits per second. From the video perspective, doing interactive chats with astronauts or something, that also pushes you out into the right-hand side of this diagram. For reference, sort of the common benchmark for planetary images is on the left-hand side, where it's marked planetary images. And I remarked earlier about the near Shoemaker mission, and you can see that shaded region is the kind of data rates that it produced. So we really do need, and in fact there are ways the DSN both is capable now and is working toward being able to move us onto the right side of that figure. And so that's from the science side, but also from the exploration side, where is the human spaceflight program going to go next? Beyond the moon, certainly. Again, I'll remind you the DSN was an integral part of providing the communications and tracking for Apollo. And looking forward, wherever the capabilities take us, the DSN has already baselined into cislunar space for the EM1 and EM2 missions, and I anticipate beyond that as well, with the idea of how do we communicate with the astronauts, how do we get the data down from their spacecraft, if they're taking secondary science payloads, how do we communicate with those spacecraft, whether it be for exploration or for science. And I think there have been already some interesting demonstrations, both on the space station and in cislunar space, of a new technology, laser communication. So actually using like the lasers that I'm using to point with, fiber optics without the fiber, as it were, to produce much higher bandwidths. And again, brings down more science data, also potentially enables better sense of presence. As I said, it's already been demonstrated in cislunar space. It's not yet been demonstrated in deep space, but the draft Discovery AO that's out on the streets now has an interesting incentive about carrying an optical communications package on it. So perhaps over the next few decades, we'll start to see optical communication coming into the DSN. We expect that optical communication will be coming in, again, in part driven by the idea of getting higher data downloads. Okay, that's my final slide. I'll leave it with that. I hope I have both provided an entertaining tour of 50 years of history, as well as giving you some thoughts about where we should be going from a science perspective and from an exploration perspective. Thanks.
Thanks very much, Joe. Fascinating. Are there questions? Okay, and please wait. Dave Morrison. Yeah, please wait for the microphone, and please identify yourself for the online people.
Hi, David Morrison, Serbi. The DSN serves so many different functions. Who pays for it? Which parts of NASA? Do the Europeans who use it? What's the source of income?
All of the above. The DSN is primarily funded through spacecraft communications and navigation, which is actually, interestingly, whatever the unit is, a division or something within HEOMD, the Human Exploration Directorate. In general, the practice has been to cooperate with our international partners, primarily ESA and JAXA, that we would provide some data downlinks for their spacecraft, and in return, something else happens. There's essentially a quid pro quo, so no payments exchange. The one exception to that is that the Indians have a spacecraft on the way to Mars, and they actually have moved into the method of saying we'll pay for DSN time.
For one or two more questions. Carly, did you? Yeah, back there. Oh, I'm sorry.
Yeah.
You have the microphone first. Yeah.
Hi, Britt Barbie, NASA Goddard. With the recent interest in CubeSat missions, What do you think the realistic prospects are for doing interplanetary science with very small spacecraft that are going to have a lot less transmitting power than conventional spacecraft?
Well, the potential is, I still think the potential is good for a couple of reasons. One is there are different modes in which CubeSats can operate. One is if there is a larger spacecraft going, I mean, sort of like, I won't flip back to it, but sort of like EM1 is going out and it's taking small packages along with it. If you can then use that larger spacecraft as a relay, which is actually a well-established technique, you know, the Galileo probe relayed through Galileo, Huygens relayed through Cassini. Actually, the Mars rovers and landers relay through the Mars orbiters. So the technique exists to do that. The other question is, you then have to also ask, because CubeSats are so, or small sats are so power limited, clearly the data rate will be limited. But maybe there are science questions that you could still do a direct to Earth, and we're also working on technologies that allow much larger stowable, deployable antennas to come out of CubeSats precisely to up the data rate.
Okay, one last question, Carly?
Carly Peters, Brown University. I'm thrilled to hear you point out the big gap of the need for high data rate for communication. This has been ignored for so long, and it's clear that this generation expects it and demands it. Without that, we're dead. So I hope things go beyond just the simple or single optical communication. That really is a key thrust, and I encourage you and all your associates to really make this bloom.
What you said, yes, thank you.
Great. Thanks again, Joe. Excellent.